So let's go ahead and get started with this week. So we're going to be talking about the diversity of samples this week, just kind of talking about different things that happen when our samples aren't similar to each other and what their different characteristics are. So I want to first talk about the fact that we talked about the law of large numbers before, but I do want to talk about how there isn't something called the law of small numbers. This is something that students may often ask about, but we don't have that because when we have small samples, they're not very representative of our population. As you remember, when we talked about having large samples, that's when we want to have large samples because they will be representative of our population. But if we have small samples, they're not going to be that representative. So a law of small numbers doesn't really make sense because we're not really trying to find out things about small numbers. And the fact that they don't give us a lot of information about the population, that's the same thing as them being unrepresentative. Because remember, we want that sample to be representative of our population. We want it to look like our population so that whatever information that we're getting from it is giving us, an accurate inference about our population itself. And then lastly, patterns in small samples can't predict larger samples basically because we can't say that that small sample is representative of our population, so we obviously cannot use it to predict those larger samples there. It's just not logical. So that's the main idea there. You'll never hear something called law of small numbers, just to kind of compare it and contrast it with our law of large numbers, which we talked about last week. Okay, so normal approximation, this is basically the basis of statistics. Whenever we have a distribution, we do want it to be normally approximated because then we can do a whole lot of different types of, different studies of it to see, what the different types of distributions they are, what it's telling us about the distribution. And once again, as we've been talking about, we repeat it often, is that we want those samples to be large and we want them to be random, because if they're large, then they're going to be most likely more representative of our population, because if you think about it, our largest sample is the entire population, so however large it is, it's going to be more representative of that true population. And then also remember, we do want to have random samples, because then that means that we're not going to have, theoretically we're not going to have bias, because they're just going to be random and chosen, without any sort of bias in them. And then this quote here, I'll just read this in regards to our normal approximation. So the sampling distribution of averages or proportions from a large number of independent trials approximately follows a normal curve. The expectation of a sample proportion or average is the corresponding population value. So all this is saying is that if you take a bunch of samples, and remember your trials are all independent, they don't affect each other. So if you take a bunch of samples, the conclusion is that it's probably going to approximate that normal curve. So it's going to have that bell-shaped curve to it as long as these samples it's a large sample and also our samples are random. And then it's just saying that our sample proportion is going to be approximately our population value. So I guess if we were to draw this out, where did I put my pen? Oh, found it. Okay, so if we were to draw this out, it's basically saying if we took a bunch of random samples and then it's a large size of these samples, it's saying it's going to make a bell curve that looks like this. And then it's saying that our sample proportion, for example, is going to approximate whatever our population proportion is, this center here. So that's all that's saying, is that we're able to make inferences about this population, so about our normal P, given our sample, because it's large enough, they're independent from each other, different trials, and then they're random. So that's all that's saying. And then these are just different equations here that we have for standard deviations of means and proportions. So basically what we're looking at here is, and I just kind of wrote out here the different, what they actually mean. So our numerator here for our standard deviation of the sample mean, that's our population standard deviation. That's what sigma means. And then square root of n. Remember, our n is equal to our sample size, just as a review. And then the same thing, standard deviation of a sample proportion, same idea there. We have our population proportion as p, and you finish that equation there to find your standard deviation of the sample proportion. And remember that our standard deviation is also known as our spread. So, that's going to be how far out from our mean we are, and that's going to be your standard deviation in that case. So that's that. Okay, so rules of the normal approximation. So this is basically saying when we have something that's normally approximated, there's certain rules that we do have to follow in order for it to make sense. So for example, and the main point here too is that our normal approximation does work better when the original distribution is close to a normal curve. So if you do have a skewed population initially, you want to make sure that you understand that it's going to be a little bit harder to get a normal approximation for your sample because your population is already skewed. So in this case, so if you have a normal, if your original population is approximately normal, then it's going to make more sense to have then your sampling distribution is going to be more normal, most likely. But anyway, these are our rules of a normal approximation. So, and here it's just different colors. Remember, when we're talking about proportions and means, these are two different things. And you can always remember too, because if you see if you have proportions, you're going to use this one because, for means, you're not going to have a p. P is going to be your proportion. So you want to make sure that you use this rule for sample proportions and these for sample means. So this first one is just saying that n times 1 minus p and n times p have to be at least 5. So that's basically saying if they are, we can go ahead forward and say that this is normally approximated. And so all that's basically saying is our successes and failures, because remember our n is our sample size, and then our proportion is technically going to be the amount of successes, so that's why n times p will be our successes, and then n times 1 minus p will be our failures there. So that's all that's saying. And then sample means, all we look at is our sample size in general to make sure it's large enough for sample means. So if we have a approximately normal distribution, then we're able, if our sample size is greater than 15, we're able to say, okay, we can go ahead and assume that this is normally distributed. And this only goes for if our original population is approximately normal, and then also we don't have outliers, it's not skewed. But if we do have, outliers, or it's looking like it's skewed, then we want to make sure that our sample size is a bit bigger. So we say 25, 30, and it just rises the more skewed it is. Because remember, when we have that large sample size, it's always going to give us, well, not always, but theoretically, it should give us more accurate information about our population as a whole. So if we have that large sample size, that's going to be more representative of our population. So if we have something that's skewed, we want to make sure we use a larger sample size in order to make sure that it's going to be representative in that case. Okay, cool. So let's do some review questions. So this first one says 30% of cell phones in King County, Washington use Sprint for their wireless service. If a random sample of 25 people with cell phones is selected in that country, then the percentage of them with Sprint service will be around 30%, give or take a standard deviation of what? So try to solve this one. If you get stuck, let me know, obviously, and we'll go over it at the end. But try to solve this one, and then we will review it. All right, let's try going over this one together and see if we can walk through it. So remember when we're talking about our standard deviation of, well, first of all, we're talking about proportions here. So we have 30%. That means that our p hat, our p hat is going to be, or our population, I'm sorry, p is going to be 0.3 because it's telling us 30% of the cell phone users use Sprint as their wireless service. So we're trying to find our standard deviation here. So we have our sample size, our n equals 25, and then we're trying to basically find the Sprint service and the what our standard deviation of this is going to be, like what our standard deviation is in general. So remember the equation for standard deviation of a proportion is going to be square root of p times 1 minus p, and then divided by n. So all you have to do is plug in the numbers here. So we're going to end up getting 0.3, because that is our proportion here, times 1 minus 0.3, and then divide that by our sample size, which is 25. So that's all you have to do is plug it in. It's about equal to 0.092, which equates to about 9.2% if you multiply this by 100. So our answer is A here. Does that make sense how we got to that conclusion for everyone? Yay. Okay, awesome. All right, and please stop me if it doesn't make sense. I'm more than happy, obviously, to go over it again. All right, let's do a second one. So retail card makes. Oh yeah, definitely. Okay, I understand. Definitely putting into the calculator can be tough. I always make sure what I do when I'm. Let me get a new. I'm just gonna put this up. So when I'm putting things into the calculator, I don't do everything at once, you know, because often people, like, if we use that one as an example, 0.3 and then 1 minus 0.3 divided by 25. So I don't try to put it all in at once. Like, the way I would do this problem is I would write it out step by step. So I'd still have my square root, and I would do 0.3 times, and then 1 minus 0.3 is going to be 0.7. And then I divide that by 25. And then I'd go back ahead, and like I said, I'm doing this step by step. So then I would go ahead and multiply the 0.3 times the 0.7. So you get 0.21, I think. I can't do mental math. Let's see. 0.3 times 0.7. Yeah, okay. 0.21, and then divide it by 25. And then I would go through this, and same thing here. I would go down here. And I'm going to take 21.21 divided by 25, so I end up getting 0.0084, and then I go ahead and take the square root of this, and you get about 0.092. So if you can see what I did here, you know, let me, is there like a highlighter on here or something? So like, see, I did this part first, and then the next thing I did was this part, multiplied those. Then the next thing I did was this part, and then I did this part as a whole. So you see, like, I took it step by step. You don't want to put the whole thing into the calculator at once, because that's going to be harder and it gives you more chance of getting an error, okay? So make sure, you know, just go slow through it, write out all your work, because then you can go back and see where your mistakes are. So yeah, don't rush through. But does that make sense, like how I go about that? Awesome. All right, cool. Good question, though. It's definitely something important. You know, understanding how to put it into the calculator is something that you want to make sure you understand, because obviously, you know what to plug in. But okay, yeah. So when you're, I'm not sure what type of calculator you have, but usually, so if it's a calculator, like some of them, if it's a scientific calculator, you have to put in your square root, the square root sign first, and then whatever number you have underneath it. But like I said, I always make sure I do everything under the square root first before I put that number there. I don't do like square root of 0.3 times 1 minus 0.3. Like, I don't put all those equations under. I find out what that center part is, and then I use whatever that number was, which was like 0.0084 or whatever. I put that in under the square root. Other calculators, and you just have to figure out what yours does, but other calculators, you can put in the number first and then hit the square root button. and then it'll give you the answer. So you just kind of have to play around and see like what happens with your calculator and how it's set up and whatnot. So, but yeah, you're very welcome, of course. All right, let's try this one. So a retail carpet business has primarily residential customers together with a few commercial customers that make large purchases. Overall, the business sells an average of 100 square yards of carpet with a median sale of 40 square yards and a standard deviation of 90 square yards. Which of the following would be the closest to a normal distribution? So this is a little conceptual. So go ahead and read through these answers. Let me know what you think. And if you're stuck, let me know and we'll also go ahead and figure that out. Great job, guys. Absolutely. So our answer here is going to be D. So as you can see here, if we look from the beginning, our population is definitely skewed to the right. So in this case, we want to make sure that we have, you know, first of all, a large sample. Because, I mean, in this case, you see our mean is much larger than our median, if you're wondering why it's skewed. So our mean is much larger than our median. We have an average of 100 square yards. That's our mean. And then our median is only 40. So that means our center technically is 40 in terms of how many different samples we have. But then our average out of all the values is 100. So since it's skewed, then for A and B, then the histogram isn't going to make a normal distribution because that's going to represent that skewed distribution. And then sampling distribution of the large yardage in the next sale, you know, you can't really tell for that. That's just kind of, you know, if it's going to be random sampling, then, you know, it's going to be random. So lastly, you do want to make sure that, so our answer would be D here because we want to check out, like the keyword here is we want this average for the next 100 sales. So that's going to take into account you know, the skewedness. And remember, for our means, we always make sure that our skewedness is, or that we have large enough sample sizes in order for us to kind of take away that skewedness and have approximately a normally distribution here, which is why D would be the answer. So great job. You guys definitely have a good grasp on that. All right, let's try another one. So this is very similar. It's the same prompt, but now we're looking for the standard deviation of the average amount of carpet sold to the next 100 customers. So this one's not as conceptual. This is more calculating. So go ahead and try this one out, and then we will review it. All right, yeah, let's write this one out. So what I do whenever I do a problem is I like to make sure that it's organized out. So I have all the different numbers that are in this big paragraph. You know, you don't want it to trip you up that it's a big paragraph. You want to make sure you're looking at it in terms of what the different values are that they're giving you. So if we read through this, so we have a retail carpet business that's primarily residential customers with a few commercial customers who make large purchases. So here we get into some of our values. So overall, the business sells an average of 100 square yards of carpet. So in this case, this is going to be our average. So mu is equal to 100 square yards of carpet. And then a median sale of 40 square yards. So we would just write median. And that's going to be 40 square yards. And then standard deviation of 90. So that's our sigma. That's our standard deviation of 90 square yards. Okay. And then now we're trying to decide what's our standard deviation of the amount of carpet sold to the next 100 customers. So in this case, remember when we're trying to find out our the standard deviation of this mean, all we want to take here is our sigma over the square root of our sample size, or I'm sorry, of our mean. So we go ahead here, and so that'll be our 100, or of our sample size. Yeah, so this is going to be our next 100 customers. So let me rewrite this out so we have the values in it first. So we have sigma over square root of n. So our sample size. So then that's going to equal, I forgot to write up here, our n is equal to 100 as well, because it's to the next 100 customers. So this is going to be n. So we have sigma over n. So what we want to do is go ahead up here. We find what sigma is, and that's going to be 90. And then what we want to do next is divide that by whatever our n is. And then if we look up here, we see that n is 100. So then divide by 100. And then all you would do here is go ahead and solve, square root of 100. And go ahead and solve this, and you're going to end up getting 9. So our answer is C in this case. And you can think of it in this way too. You know, if you think of it logically, it says they have an average of 100 square yards, median of 40, okay, standard deviation of 90. So if it would make more sense for it to be, you know, you wouldn't want it to be as small as 0.9, because if you look at the numbers that they were using, those numbers aren't going to be necessarily conducive to having such a small standard deviation there. It seems like the spread will be a little bit bigger, but that's how you would find it. So like I said, I always go ahead through, the first thing I do with problems is go ahead and write out everything that I have and make a list of it so that I can refer back to it, you know, when I'm actually doing the equation. So, and then I also make sure I write out the original equation with like the symbols in it too. So that's the main idea there. Does that make sense how we got the answer of C there? Awesome. I know everyone says that. They're like, yeah, when you do it, it's cake. But the more you practice it, it'll definitely get easier. And like I said, think of it logically too. When you get your answer, think, does this make sense? So I would definitely try doing that. But okay, I'm glad you guys get that one. All right, let's try one more. So we would like to use a normal distribution to calculate the chances about how a sample average might turn out. In which of the following situations would the normal approximation work the worst? So it's kind of a weird wording, but basically like which of the approximations is like not, which of these sample sizes would not be good and whatnot for each histogram. So try this one out. Okay, good job, guys. So if we look at this one, let's see. So our answer is B, because remember, so this is saying which of them would work the worst. So as you can see, our histogram 1 is looking approximately normal, while our second one is going to be skewed. It's actually right skewed. So really the main thing we want to be looking at initially is just like, okay, the second one's skewed, so probably, that's going to be the one that works the worst in either case. So we can kind of cross out C and A because they're talking about histogram 1, which is normal. So either way, that's probably going to work at least somewhat okay. But then remember, we're always going to have, so good job, narrowing it down to B or D. But then remember, our sample size, whenever it's the smallest, our small sample sizes are not going to give us as representative of a sample. So B is going to be the worst because it has the smallest sample size out of all of them, or out of, between D and B. So since it's going to be that low, large or small sample size, so not that representative, and it's a small sample size on a skewed distribution. So that's like, no, we don't like that at all. So our answer is B there. Okay, good job. Looks like you guys understand that one. All right, so that's all we got for tonight. So go ahead and obviously watch this and the other ones back on the YouTube channel. I hope you all have access to that. And then our next review session, I believe it's for the midterm, is going to be next week, the 2nd. Don't quote me on that, but I'm pretty sure. And then if you haven't already given me your Penn State ID or email, go ahead and put that in the chat box. I think everyone did give that to me, though, but thank you so much for that. If you guys have other questions, feel free to type them into the chat box. But if not, you guys are good for tonight.